So today we're going to talk about capacitors, and the symbol for a capacitor is just two parallel plates of metal connected to wires that go up and down. And this should be familiar from maybe a previous physics class, but let me say a few words of reminder here. So if you have a voltage source across a capacitor, let's have a voltage source, then there'll be positive charges that build up on one plate and negative on the other. Now, I'll say two words before we start. All electrical components in circuits are always net neutral. There's never a circuit component that we'll use where it'll build up some net charge and it'll make your hair stand up on end or something. So what's happening here is that as positive charges come onto the top plate, they repel positive charges in the bottom plate, and those positive charges leave. And so you're left with a net negative charge. You know, maybe what's actually happening, you think about in terms of electrons. Electrons are going to come up and build up on this plate, and they're going to repel electrons out of the metal on the top. Those electrons are going to leave the top. We'll always talk in terms of positive charges. So everything is always net neutral. The components are always net neutral. And what this means in particular is that if we think about the currents coming in, some current coming in and some current coming out, these currents have to be the same because no net charge is going to build up anywhere. And you might think, well, if there are two parallel plates here, there's a gap between them, either a piece of air or insulator. If I put charge in here, how are the charges coming out? Well, it's not the same charges, not literally the same electrons that are moving across this gap. But again, it's this effect here where some charges come on this plate and they push away like charges on the other plate, and those charges keep going. So that's our fundamental picture of capacitors. All right, now, what is the picture of a capacitor in our water analogy? Well, the fundamental thing we'll be using over and over again today is that the amount of charge on a capacitor is just proportional to the capacitance and the voltage across the capacitor. So this is the charge on a capacitor. This is plus Q. This is the voltage across the capacitor. And you can think about this like a tank of water. So again, if voltage is the height of the water, so here's some water level, the voltage has to do with the height of the water. And the amount of charge, if current is the flow of water, then charge is just, you know, the water itself. Then what is capacitance? Well, in a tank, I would say that the best analogy here is the area of the bottom of this tank. So C is like area. And that way the total amount of charge here is proportional to the area of the tank times the height. So I would say that one thing that's confusing about the name capacitor is it seems to have something to do with capacity, maybe. And so people might think about it as, you know, some closed volume and you're filling up some capacity. That's not really the right way to think about it. For an ideal capacitor, this tank can be infinitely tall. You could put more and more and more charge in, and the voltage just goes up and up and up, and everything is fine. Now, in a real capacitor, eventually there'll be a spark across this gap, and so you can't put an infinite amount of voltage on. But that's a problem with the physical implementation of the capacitor, because these plates have to be close together. You can make a spark. But the best way to think about it is just this tank that holds water, and the wider the tank, the bigger the capacitance. And you can imagine putting water in with a little spout that's coming into the top here, and taking water out the bottom. Here's a little spout that comes out the bottom. And the water that comes out the bottom is at a lower height, if you want. You know, if you actually charge a capacitor, you're basically always putting water right at the top water level and taking water out right at the top water level, right? Because this conductor here, the voltage of this conductor here is always at the top. So you're always just putting water in right right there and taking water out right there. So, okay. Now let's talk about current. What is the relationship between charge and current? Well, current is just the rate of flow of charge. So if I were to take the time derivative of this equation, the time derivative of the amount of charge in the capacitor is just the current coming in to the top of the capacitor. So as I put current into the top of the capacitor, charges build up. And the rate of change of those charges is the current. So the time derivative of this equation is just current equals C times the time derivative of the voltage across the capacitor. And that'll be the other thing we use over and over again. All right, so let me talk about our first circuit with a capacitor in it. And the first circuit is very simple. There's just some voltage that will come in that we will control. And it'll go through a resistor and then into a capacitor and then ground. So here's our R, here's our C, and we'll measure V out there. Now let's imagine that the capacitor starts out empty and our V in is going to look like this. It's going to look like 0 volts for a while, and then we'll do a step where it goes up to some V naught, say. And this is V in as a function of time. And let's calculate what V out is as a function of time. So this will be one of the only times in this class where we sort of really write out the differential equations and actually solve things pretty explicitly. Now, what we have to think about is if this is our equation for a capacitor or its time derivative I, let's start identifying some components here. So in this equation, this is the charge on the capacitor and the voltage across the capacitor. So this V is going to be the voltage across the capacitor. So the voltage across the capacitor is just V out. That's how much voltage is across the capacitor compared to ground. And the current is in this equation, it's the current that's going into the capacitor. And any current that goes into the capacitor also has to go through this resistor. So there's only one current in this equation. You know, a V out I'm just measuring. I'm not actually stealing any current in the output. So all the current that comes into through here goes through the resistor. Same current goes through the capacitor. Same current goes into ground. And again, it's not literally the same electrons because they can't jump the gap. But when charges build up here, it will repel like charges away. All right. So this current here, let me just write this equation here. This is I equals C D, and now I'm going to be more explicit here. I'm going to label this V out dt because we have more than one voltage. I have to be a little careful here. This current, since it's the current that goes through this resistor, we also know that V equals IR. And what does this mean? This is the voltage across the resistor and the current through the resistor. So the current through the resistor is I. And if we were to solve this in terms of the voltage across the voltage across the resistor is the difference between V in and V out. So I could write that this I here, if I look at the resistor, this is going to be V in minus V out over R. All right, so now what am I going to do with this? Let me solve for V in, actually. I think it's a little bit easier. So I'm going to multiply through by R and move V out over to the other side. So V in is going to be our driving force, our driving potential. And this is going to equal RC times the derivative of V out dt plus V out itself. Now, all these things depend on time. And let me take us, before we actually solve this equation, let me note that this RC here, the units on RC have to be units of time. in order to make the units of this equation work out, right? This is units of volts. This is units of volts. We're adding that to something that has to have units of volts. This is a volts over time, so therefore RC has to be time. And in fact, an ohm times a farad equals a second. So that's our unit of time. So we'll typically deal with kiloohms and microfarads, and we'll get times that are milliseconds, say. Okay, so there are lots of techniques to use to solve this equation. I would say the simplest is just to use your intuition or your history or some sort of guessing of a solution. And I'll just write down the solution and we'll justify it in a second. So this is a linear equation in V out with some forcing term. So let me just write down a solution and we can check it in a couple different ways here. So V out is going to equal, well, this is V out as long as t is bigger than 0. This is going to equal V naught times 1 minus the exponential e to the minus t over RC. Okay, so let's check a couple different cases. So this only applies for t greater than 0. So for t less than 0, nothing has happened yet. So the voltage out is just going to be 0, just like the gin. So 0, 0, 0, 0, 0. Now the input switches on. And what happens right at t equals 0 in this equation? Well, if I plug in t equals 0, I have 1 minus e to the 0. That's 1 minus 1, that's 0. So right after the input switches on, I'm still at 0. And as time goes on, this second term is going to get smaller and smaller and smaller. So it's not going to cancel as much as it used to cancel. So this is going to slowly tend toward V naught. And as I let t go to infinity, this is going to asymptote out to 1 minus e to the minus infinity. So it's going to asymptote out to 1 minus e to the minus infinity. So it's going to asymptote out toward V naught here. And the key here, the thing that sets the time scale of this is RC. So if I look at RC here, RC is going to be the point in time where this has gotten most of the way to where we want to go. In fact, I think it's something like 63%. So if you just plug in 1 minus 1 over e, you get something like 63% of the way to V naught. So whenever we build a circuit with R's and C's, the very first step is just to calculate RC, and that will set the time scale for everything else. So all the measurements you're going to make, all of the frequencies you're going to deal with, RC is the thing that sets the time scale. So with your signal generator and your oscilloscope, you can go from times that are seconds all the way to times that are milliseconds, microseconds, nanoseconds. There's just an enormous range. And so where do you even start looking? Well, unless you're looking at times that are roughly this order RC, you're probably not going to be looking at the right thing. So this is our first example here. Let me draw what happens when you put in a square wave rather than just a single step. And while I'm erasing, you can feel free to ask questions here. Okay, so let me go back to my blue marker here. Let me draw my input as a symmetric square wave be in, symmetric around 0. And I'm not going to go through the math to resolve this equation, but the intuition is still the same. In 1 RC time, we're going to go from wherever we are up to 63% of the way to where we're going. So at every time step, we're going to be shooting toward. So let's say that this has been 0 for a while, and now we're going to switch it high. We're going to shoot up toward the top. Asymptote, that's maybe not the best asymptote ever. So asymptote up toward the top. And then now the input's going to go down, and now we're going to shoot down. Eventually asymptote. We're going to shoot up. Asymptote. And if I asked you how fast do you need to run this square wave in order to see this picture, well, sort of one RC is somewhere around here. So you probably want the period of this square wave to be, I don't know, maybe 1, 2, 3, 4, 5, 6 RCs to see a full period of this square wave to give you this picture. So let me go over to my demo here. In my demo, I've picked R to be 1 kilo ohm and C to be 1 microfarad. And so RC, this is 10 to the plus 3 and 10 to the minus 6. This is 10 to the minus 3 seconds, or 1 millisecond. And so I'm going to put in a square wave that's slower than 1 kilohertz, or maybe a tenth of 1 kilohertz square wave. So let me switch over to the other screen and show you what's going on there. Okay, connect. All right. Calibrating. Oh. All right, so I'm going to use 2 different things. One is the signal generator to make the signal. And I have 2 channels here. I have channel 1 and channel 2. Now, my biggest complaint with Scopy is actually channel 1 comes out the yellow wire, and channel 2 comes out the yellow wire with the white stripe. I don't know why in the signal generator they're colored orange and purple just like everywhere else. I wish they were colored yellow, and I wish they had picked a different wire for channel 2. We're almost never going to use channel 2 output, but channel 1 output, okay, you could turn it on and off, and you can get settings, either show the settings or don't show the settings. So my settings, 5 volts peak to peak, that's fine. And my frequency, 10 kilohertz, I'm going to lower that a little bit. And you can either type specific numbers of hertz here. Let me point the microphone a little closer to me. You could type numbers of hertz here, or you could use this control here, especially if you have a mouse wheel, or maybe if you do a double finger or something like a scroll. You can change it from, basically 1, 2, 5, 10, 20, 50, 100, 200, 500. These are roughly equally spaced logarithmically. It's kind of like how money works, especially euros. They're nice and equally spaced logarithmically. So it's much better than typing in random numbers and having to change the units every so often. So let me go down to 100 hertz for my frequency. Offset, that just shifts things up and down. I want no offset. Phase just shifts things left and right. I want no phase. Duty cycle means what percent of the square wave is on. So I'm going to just keep that at 50%. Noise, none. So you can add a little bit of random noise if you want that. That's not usually something we want. And then run. So run, it'll actually turn it on. Okay, now let me switch to the oscilloscope here. And right now I am showing nothing. And let me see why that is. So both channels are in fact turned on. And let me look at the trigger. My trigger is auto, that's fine. My level, I'm going to make that 0 volts. 0 volts. This is all fine. Let me look at my settings here. So my settings, my time is set to 10 microseconds. So again, we calculated the time scale for the particular capacitor and resistor we have. The relevant time scale should be about a millisecond, not 10 microseconds. So let me go up to a millisecond or so. My volts per division, let me zoom out a little bit. Oh, I have to run. That's part of the problem. Okay, run. There we go. Okay, so let me do 1 volt per division for orange and 1 volt per division for blue. Okay. Now what you see coming out in orange isn't the world's nicest square wave. And actually the reason why that is because when it first switches, a huge amount of current has to flow to get this capacitor to charge. So it's not really able to maintain this 5 volts super, or I guess 2.5 volts. It's 5 volts peak to peak. It's not able to maintain this super well in the beginning. So it takes a little bit of time to level out. But you can see the pattern here. So it's going to asymptote up, asymptote down, asymptote up, asymptote down. Now, you can change the time base, the horizontal zoom. I can zoom in or zoom out. Let me zoom out a little bit. Let me go back to the signal generator. I can make this go a little bit slower. So instead of 100 hertz, I can go down to 20 hertz. And now there's plenty of time for it to come to a asymptote. So let me go back to 1 millisecond. So this time base means the time per box, time per division. Turn off the settings here. Let the settings off. So each of these boxes is 1 millisecond. And what that means, and this is also our RC, time constant. So after 1 millisecond, we've charged up to, I don't know, maybe that's about 63% of the way up to the top. It's a little bit more than 50% of the way up to the top. And after another millisecond, we've got another 2/3 of the way up. And after another millisecond, we've got another 2/3 of the way up. So that's pretty much how this works. Let me stop sharing for a second and show you something else, which is pretty useful, but it was hard to see the way I did it the first time. Uh-oh, come on, stop share. Why can't I stop sharing? Can you still hear me? Somebody say something.
I can hear you.
Okay, so the computer's not frozen. Something else weird happened. Let me share my whole desktop. So am I sharing now? Am I sharing the whole desktop screen? So now it just looks like a small window on a big desktop?
Yes.
Okay. So one thing you can do that's kind of nice is you can take these things and peel them away. So I'm looking at the oscilloscope, but I want to take my signal generator. I'll just grab the button, drag it into the center. And I don't know if you can read the text, but it says detach. And so if I let go here, it'll actually turn it into a second window of just the signal generator. So now you can have both of these going at the same time. So let me run my oscilloscope. I can turn my signal generator frequency up while I'm watching the oscilloscope. So I'm going faster and faster and faster, slower and slower and slower. So you have to keep these things in mind. The frequency of the input and the scale of this input, which never changes, it just always looks like a square, versus the frequency and the scale of the output. So let me zoom in. Let me go a little bit faster. And let me go a little bit faster on the oscilloscope here. I can make these windows nice and wide. So notice that if I go fast like this, it doesn't really have enough time to get very big or very small. And you just see this linear part here that's going up and going down and going up and going down. Now this is going to be our next circuit that we talk about. It looks exactly the same, but it's going to be an approximate integrator. So if you think about the integral of a constant positive number, well, the integral of a constant positive number is something with a constant positive slope. And the integral of a constant negative number is something with a constant negative slope. And then a constant positive slope, constant negative slope, constant positive slope. So for the case where we don't allow the output to change very much, this circuit acts like it's a pretty good approximation to an integrator. And let me show you some other examples. So let me change the waveform from a square to a sine wave. So the integral of a sine is a cosine. So you can see that. It's actually a negative cosine here, the way it's triggered. I can change it to a triangle wave. And it's a little bit hard to see here, but the integral of a constant line is actually a parabola. So there's little parabolas going like this, and then a parabola going the other way, parabola going the other way. So I don't know, these are the trapezoid. I don't know what's going on there. No, let's just stick with square wave. And if we could see, yeah, frequency of a kilohertz or something. So yeah, basically sine wave, square wave, and triangle wave are the only interesting ones that we'll build an approximate integrator and an approximate differentiator as two circuits here. So getting practice with the signal generator and the oscilloscope is a big part of today. Let me say a few more words about the oscilloscope, because some of you have probably used these before, either in E79 or in some other context. But the trickiest part of oscilloscopes is always the triggering. So let me go a little bit slower here with my input. And let me talk about the triggering of the oscilloscope. So in the trigger menu, I can trigger on auto or normal, and I'll show you what the difference between those in a second is. Okay, right now I'm triggering on channel 1. So what does triggering mean? Well, in the old days, in the analog oscilloscope, it would wait around until one of the channels crossed some threshold going in some particular direction. And nowadays in digital oscilloscope, it's basically the same thing. You're waiting for some channel to cross some threshold in some direction, and that shows up at the center of the screen. So right now we're waiting for the source, channel 1, this is in the trigger menu. The trigger source is channel 1. The condition is rising edge. So we're waiting for channel 1 to rise through the level of 0. And this hysteresis is just to avoid some noise in case it sort of jiggles around 0. You don't want it to jump around a lot. So this is a little bit hard to illustrate in channel 1. Let me switch to channel 2. So right now I'm triggering on channel 2, and I'm still waiting for channel 2 to rise through the level of 0. And now you can see that's exactly what shows up at the center of the screen. It's channel 2, the purple channel, rising through 0. If I change this to falling edge, now channel 2 is going to fall through 0, and that's what shows up at the center of the screen. We go back to rising edge. And I can change the level here by moving this up and down a little bit. And changing the level to 1 volt or minus 1 volt. Oops. See, when it's jumpy like this, it's not catching it very well. So whenever there's jumpiness like this, it means the triggering isn't working very well. So often that means changing some of these settings here. So if you'll notice that on the side, the trigger level is actually this slider here. So I can change the trigger level by grabbing this thing and sliding it around, and the level reflects this. So let me set it back to somewhere around 0. I can actually type in 0 if I wanted. And now let me show you the difference between auto and normal triggering. So normal triggering and auto triggering, right now it's not doing anything different. The difference really comes when I don't get a trigger. So here I'm not getting a trigger. And I don't know if you can tell, but it's just not updating the screen. So normal trigger just means wait until you get a trigger and then start drawing. Auto means wait until you get a trigger and draw, but if you don't get a trigger for a while, just draw it anyway. So there, now I'm on auto. So it's waiting for a trigger, but if it doesn't get a trigger, it'll just draw it anyway at some random time. And so if you're getting random jumping around stuff, that means you're not triggered. So you have to look, okay, I'm on channel 2, my level is too high. Let me set the level such that channel 2 actually crosses that level. And that's separate from moving the whole waveform up and down. So I can move the whole waveform up and down just to put something on top of something else, as opposed to I can rearrange the screen like this. Now you have to be a little bit careful because the zero level is not super well defined. And if I switch my trigger channel to channel 1, it'll move my trigger down here. And changing the level on channel 1 doesn't affect things very much because this transition from low to high happens so quickly that changing the level doesn't affect things. But if I go off of channel 1, there I'm off the orange, now it has nowhere to trigger on. So since I'm on auto, it'll just pick some random time and draw it. So that's how triggering works. So let me pause and ask for questions there, and then I'll switch back to the lecture. I'm going to write in yellow the approximation that makes this circuit act like an integrator, not for a step, but for any input. And the approximation that we're going to use, so this is called an approximate integrator. Approximation we're going to use is that as long as the magnitude of V out is much, much less than the magnitude of V in, this circuit's going to act like an integrator. The output is going to be proportional to the integral of the input. And where does that come from? Well, if we look at this equation that we had before, as long as the magnitude of V out is much, much less than the magnitude of V in, we can ignore this term here. We can approximate this as approximately 0. And what this means is that V in over R is approximately C dV out dt, or if I rearrange terms here, let me go over here. So let's see, dV out dt is approximately 1 over RC V in. Okay, so units still make sense. This is a voltage over a time, a voltage over a time. And if the derivative of the output is proportional to the input, that means that the output itself, V out, is going to be the integral of the input. And we can be formal here and put a T prime and dt prime and integrate from 0 up to some T. But as long as you keep the output voltage small, the output is proportional to the integral of the input. And it has to be proportional because the units have to work out, right? This is a voltage and dt is the time, so there has to be a 1 over time as the constant of proportionality, and that constant of proportionality here has units of time. All right, so this is the math behind how we can get an approximate integrator. In a couple lectures, we will build a circuit with an op-amp that's basically an ideal integrator. You don't need to keep the output voltage tiny. It'll integrate any voltages to be any other voltages as long as it stays within what the power supply can provide. And the integration is going to be much more exact. But this is a building block for that integrator. Understanding that one, you need to understand this one first. So, okay, that's the approximate integrator. There's also an approximate differentiator. Let me draw that circuit. And I'm not going to go through all the math. I encourage you to go through the similar writing out an equation that looks a lot like this on your own as you do the lab. But let me erase the stuff that we're no longer using here. So just sort of as a sidebar, this is the approximate differentiator. There's a V in. And the only difference is we just switch the order of the C and the R. So C on top, take the V out from the center, and R on the bottom. And again, when you hit this part in the lab, I encourage you to go through some of the math, but what you'll see is that V out is approximately equal to RC times the time derivative of V in. Again, for the same approximation for V out small compared to magnitude of V in. So, all right. And again, when we get to the op-amp labs, we'll see a more ideal version of this differentiator. But you can put in various signals, like you put in a triangle wave, and the derivative of straight lines are constant positive and constant negative. You could put in a sine and get a cosine, put in a cosine, get a sine, or you could put in a square wave. And let me ask before we go on, what is the derivative of a square wave? It's a little bit tricky here because in the regions where things are constant, the derivative is going to be 0. But in the regions where we have a sudden jump, the derivative is going to be really big and positive or really big and negative. So the derivative of a square wave is going to look like 0 with a positive spike, 0 with a negative spike, 0 with a positive spike, 0 with a negative spike. And of course, if it were a true, perfect, absolutely ideal square wave, these would be delta functions that would be infinitely high and infinitely thin. But for any real square wave, they're going to be finite size spikes that are just really short in time and really, really high. So that'll be one of the first circuits you build. So the next thing I'm going to talk about is filters. So resistor capacitor filters. Filters and frequency response. So this whole section here, when we say the frequency of a signal, we always mean the frequency of a pure tone, frequency of a sine wave, sine waves only. And if you've ever listened to sine waves versus square waves or triangle waves, the sine wave sounds like a much purer tone. And there's a good reason for that. If you do a Fourier decomposition, a sine wave contains a single tone, and a square wave or a triangle wave contain a sum of many pure tones, many sine tones. Why do we build things out of sines and cosines as opposed to building things out of some other random wave? Well, the basic idea is that when you have a circuit like this that only involves resistors, capacitors, and inductors, when it involves only linear elements, if you put a sine wave in, you get a sine wave out. And that sine wave might be scaled and it might be shifted, but sine waves in lead to sine waves out. And that's a super important thing that makes sines the thing that we focus on. And let me say that if we write a voltage as a function of time, if we write this as some V naught cosine of 2 pi times frequency times time plus some phase offset phi, it's called phi naught. A lot of times it's convenient to write this cosine as the real part of a complex number, V naught E. Well, before I do that, let me call 2 pi f omega. So that's a pretty common and angular frequency. So f is the real honest to God frequency that you measure in hertz, and that shows up on your signal generator and your oscilloscope. And omega is radians per second, which is only convenient because I don't have to write 2 pi over and over and over again. This is cosine of omega t. You could write this as the real part of e to the I omega t times e to the I phi naught. Okay, so already you see one advantage of writing things as complex exponentials. You know, obviously there's a huge disadvantage, which you have to think about complex numbers, and that's more work than thinking about real numbers. But one way to implement phase shifts here is just to multiply by a complex number. So if you have a cosine that's not phase shifted, and you multiply that by e to the I phi naught, you're going to shift that cosine over. So a cosine that starts off at 0 is going to shift over to be a cosine that starts off a little bit earlier. So one advantage of complex numbers is that phase shifts are just multiplying by a complex number. And the second advantage is that derivatives are easy. So the derivative of a cosine is minus a sine, and the derivative of a sine is a cosine, and there's a little bit of messiness going on. But the derivative of e to the I omega t, this is just I omega e to the I omega t. So whenever we take the derivative of a sinusoidal thing oscillating at some particular angular frequency omega, it's the same as just multiplying it by a complex number. So we can shift the phase by multiplying by this complex number. We can take a derivative by multiplying by that complex number. These two more complicated mathematical operations become simple when we deal with these complex numbers. And so we're going to turn all of our beautiful real sines and cosines mathematically into the real parts of complex numbers. And we're going to do a bunch of math with the complex numbers. And at the end of the day, we can take the real part and get back sines and cosines. So that's the whole idea of this thing called impedance. So it's a generalization of resistance for the case of sinusoidal signals. Sinusoidal. So in general, we want some sort of, instead of V equals IR, we want V equals I times something that's like a resistance, which we call Z. And for a resistor, Z of a resistor is just the resistance. That's easy. For a capacitor, Z of a capacitor is going to equal 1 over I omega C, except I'm going to call it J omega C because we're going to use I as a current a lot. So instead of the complex number I being the square root of -1, we're going to call that J here in electronics. And for an inductor, we'll see this next time, the impedance of an inductor is going to be J omega L in the numerator. All right, so let me talk about, one, where do these things come from, and two, how do we use them? So I guess I'll keep this box here. So where does this come from? Well, if we start with our fundamental relation for a capacitor, where Q equals CV, and I, the current, I equals C dv dt, if we promote both of these into complex numbers, and I say, well, let the voltage across the capacitor be some e to the, well, let me give it some amplitude here, some v naught e to the I omega t. So let me do this in 2 steps here. Let me just press on for a second here. All right, so what is dv dt? Well, this is just v naught. Let me call this j omega. Sorry, this is v naught that comes along for the ride, j omega from the derivative, e to the j omega t. And if I let the current I of t be some I naught e to the j omega t, then I can equate both sides of this equation here. I could say, all right, well, I naught e to the j omega t equals c times this time derivative, v naught j omega e to the j omega t. And a lot of stuff ends up canceling out. And I get, if I solve for v naught here, v naught, am I off the board? Yeah, I'm off the board. Let me go back up here. If I solve for v naught, I get v naught equals I naught times 1 over j omega c. So this looks a lot like v equals IR, where my R, the thing that looks like resistance, the thing that relates the amplitude of the current to the amplitude of the voltage, is this 1 over j omega c. So that's where my impedance of a capacitor comes from here. And how do I use this? Well, I'm going to use this by treating this circuit here and circuits like it. I'm going to just treat this like a voltage divider. So now I have things that, as long as I'm only dealing with sine waves, I can treat them like resistances that vary with frequency, and we'll consider the magnitude and the phase separately here. So let me rewrite this circuit down here. Let me rewrite it as if it is a V in, a sinusoidal V in, and a resistor that I'm going to write like this. There's some impedance that has to do with the resistance, and some impedance that has to do with the capacitance, and then ground. I'm going to take this as V out, which also has to be a sinusoidal wave. And just from my voltage divider equation, I can just write, what is V out? Well, V out is going to be a fraction of the way that I am up from ground. So if I go up by Z of the capacitor, how far am I up? Well, I'm Z capacitor over the total times V in. That's what fraction of the way I am up. So that should be familiar from last time. And now we can consider limits here. So limit as the frequency goes to 0. Well, omega is going to go to 0. And what's going to happen to the impedance of the capacitor? Let me rewrite this a little bit more. Impedance of the capacitor, 1 over j omega c, ZC is going to go to infinity. And if ZC is going to infinity, then in the denominator, I basically have something huge plus something finite. This is just R. And if I have something huge over something huge plus something finite, as I take that limit, this is just going to go V out, just going to go to V in. And as the frequency gets really high, f goes to infinity, omega is going to also go to infinity. CC, oops. CC is going to go to 0. And if ZC goes to 0, I have something going to 0 over, basically over just R. So V out is going to go to 0 in this limit. So if I plot the frequency response here as a function of frequency, when frequency is 0, my V out is V in. And as the frequency goes to infinity, I get lower and lower and lower and lower. We're going to have some transition from V in down to 0. So this is V out. Okay, so now the interesting thing happens. We always ask what happens when these things are about equal. So that when you're dealing with impedances, that's a slightly different situation. So before, when we had only resistances and these things were equal, V out was half of V in. Let's actually work out the case here when these are equal. Now they can never be identically equal because this one involves a complex number and this one doesn't. So let's ask what happens when the magnitude of the resistor's impedance equals the magnitude of the capacitor's impedance. So implies what? Well, the magnitude of the resistor's impedance is just R, and the magnitude of the capacitor's impedance is just 1 over omega C. So first of all, this gives us a condition for omega. Omega is 1 over RC. And remember, omega was 2 pi f. So if we solve for f is going to be 1 over 2 pi RC. And you may remember that this is called the corner frequency. So let me put a subscript C here. So at some special interesting place, this is about where these impedances are equal. Let's actually work out what happens to V out. Let me get rid of all this stuff here. So this will be the last thing I do before I set you off on your lab. So let's see, at the corner frequency, when f equals the corner frequency, or 1 over 2 pi RC, what that means is that we have V out equal. All right, now remember, I think the easiest way to do this is to remember that when this is true, it means that the magnitudes of these things are the same. So ZC, its magnitude is going to be R. So I'm going to have R over J divided by R over J plus just R, V in. And all the R's are going to cancel. So, and I can move the I's up and down as much as I want. So let's see, what do I want to do here? I guess I'll multiply top and bottom by J. So here I get 1 over 1 plus J V in, right? So now this is a complex number, and I can write what this complex number is. It has a magnitude and it has a phase. If I calculate what the magnitude and the phase are, what I get is I get this magnitude is 1 over square root of 2, and its phase is e to the minus I 45 degrees Vn. So I'm going to not worry about the phase so much, but the magnitude is 1 over the square root of 2. So what that means is at this special place, at the corner frequency, Fc, the magnitude is down by square root of 2. So this is Vn over square root of 2. So above this corner frequency, you start to get much lower amplitude. Below this corner frequency, you get closer and closer to Vn. This is kind of where the transition happens, where the magnitudes of the impedances are the same. There's another name that the book gives this, which maybe you talked about in your previous class, and that involves decibels. So let me remind you the motivation for decibels and what this particular thing is called in decibels. All right, so where do I want to go here? Okay, so the history of this is that, you know, back when the telephone company was first getting started, they were putting audio power into telephone lines and measuring the audio power that came out of telephone lines. And so the ratio of the power out to the power in was an important concept. And oftentimes these vary greatly if you're going over long distances. So oftentimes they would take the log base 10 of this power, and this was some number of bells. So the ratio of the power out to the power in was some number of bells, named after Alexander Graham Bell, who invented the telephone. Okay, so what's a decibel? Well, it's a tenth of a bell. So if we wanted the number of tenths of a bell, we'd have to multiply this by 10. Log base 10 of power out over power in. And this is all fine and good if you care about power. Usually we're not measuring power, we're measuring voltage. But remember that power is V squared over R. So I could write this as 10 log base 10 of V out squared over V in squared, and the R's are going to cancel each other. And I could bring this 2 out of the log. This gives me 20 log base 10 of the ratio of V out over V in. And this is some number of decibels. Okay, so what is our ratio here? At this corner frequency, the ratio of V out over V in is 1 over the square root of 2. Right? And if I take 20 times a log base 10 of 1 over the square root of 2, I get minus 3. You know, minus 3.0 something, 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 but it's about minus 3. And so another name that the book gives to this corner frequency is the minus 3 dB frequency. So this corner frequency is sometimes also called F minus 3 dB, because it is where you are down by a factor of square root of 2. And if you convert 1 over the square root of 2 into decibels, you get minus 3. So I don't know, hopefully that was a little bit of review, but that's where some of this stuff comes from. And that's a notation that the book uses sometimes. They don't call it a corner frequency. They usually call it a minus 3 dB frequency. But it's all the same thing. All right, so I will send you off on your way. This was a low pass filter. If I were to flip the resistor and the capacitor, just like I turned an integrator into a differentiator, I'm going to turn a low pass filter into a high pass filter. That basically has the opposite opposite characteristic here. It'll climb until the 3 dB point, and then asymptote up to the voltage in. It'll pass high frequencies and block low frequencies. High pass filter. But the 3 dB point is the same point. And the plot that I've made is a plot that's linear in frequency. You make a plot in log of the voltage and log of the frequency. You get shapes that you may be familiar with from stems. And we'll do that today too, as a review and as practice using the instruments and in practice using Scopy. So this looks like some sort of crazy, beautiful mind pegboard here, but are there any questions that any of you have before you launch into the lab? All right. This, I will say, this is probably the most mathematically intense lecture. The rest is going to get simple again. The concepts might get a little more complicated. The components are going to get more complicated. You have to think a little bit more abstractly, but just in terms of like raw plugging in numbers and doing math, this is the worst.